All right, now let's see. Come back to where we were roughly. Okay. And let me cut off the camera here. There we go. Okay. So I think we went a little bit past this, but these are the systems A, B, C, and D that your book divides a vapor. And when you say vapor, that kind of connotes that we're going to have evaporation and condensing. Okay. If you have like a gas plant, a Brayton type cycle, you don't use the term vapor unless you have the phase change. Just kind of, so we went through these systems last time. So this system B, which includes the boiler, turbine, condenser, and pump, that section, those four components are what is defined as the Rankine cycle. And then, of course, we saw the kind of embellished cycles that TVA was running. And so, to enhance efficiency, we can start adding feed water heaters and other things inside that box, but that's all part of what we mean by the Rankine cycle. Oh, these slides have this little blue ball that likes to run around in circles. So anyway, I guess that's okay. I don't know how to program it. Okay, so first law of thermo, just kind of to refresh a little bit, requires that net work developed by a system undergoing a power cycle equals to the net heat. So as long as it's a power cycle, then we can draw these types of little guys over here where we've got some sort of a hot reservoir and we transfer heat into the system. This could be done by a boiler per se. And then everything's in the system and work, could be the electricity, it could be a spinning shaft, whatever, exits. And then we reject some heat to the surroundings. So net heat would be Q in minus Q out. And of course, the net work of the cycle is the work developed. So thermal efficiency for this is going to be just the net work that comes out of the cycle. And that's net. So when we get inside the box, we may have a turbine and generating and a generator producing work, and we may have pumps and things like that consuming work. So W dot cycle is the net that produced minus that required to operate the cycle. And Q dot N is the heat that's transferred in to the system to, say, to vaporize the working fluid. Second law, if we want to remember those days, a thermo requires that the thermal efficiency be less than 100%, which basically means that we have to reject some energy to the surroundings. We can't have, second law tells us we can't have 100% conversion of this heat transferred in, this Q dot N, into work. That's theoretically impossible. Typically, maybe up to 40% on some traditional power plants. We'll see that combined cycle plants, which puts a Rankine cycle with a Brayton cycle, can get up into the 60s, which is much better. We can do cogeneration type systems and get well up into the 60s or 70s. So there are options, but just the big Rankine cycle power plant that's operating today, it's going to take a supercritical, really high pressure unit to approach 40%. Most of them these days, with all of the emission cleanup equipment, scrubbers and all that stuff that have been added, that have parasitic pumps and fans and all that stuff to allow the cleanup of the gases, has dropped the efficiency probably to the 30, 31, 32%, maybe even into the high 20s, depending on the cycle and the load as we operate them at closer to 100% load, the efficiency goes up a little bit. Okay, so there's a couple of paragraphs here that really are important, and this is one of the key bits of information that we're going to be talking about the rest of these slides, and really it kind of underpins all this Rankine cycle discussion. So thermal efficiency tends to increase as the average temperature at which energy is added by heat transfer increases. So if we can get the energy to come in at a higher temperature, even the same amount of energy and all other things being equal will increase the cycle efficiency. And or the flip side of that, which kind of does the same thing, if the average temperature at which energy is rejected in the condenser by heat transfer decreases. Well, so that temperature is really set by the environment. And so whereas these are thermodynamically true, sometimes it's hard to implement because on the high temperature side, we usually run into material limitations. You know, yeah, we'd like to do this hotter and inject the heat, but the problem is the boiler tubes burn out too fast, you know? So we have material limitations on the high temperature side. And on the low temperature side, how do you get the lake to be colder? That's a pretty good trick, you know? Now, you know, we do know in the wintertime, like at Kingston, it's sitting there on Watts Bar Lake. Well, Watts Bar Lake is colder in the wintertime, a few degrees. And guess what? Kingston's a little more efficient in the wintertime because the temperature in the boiler is probably not changing. And the temperature of the lake, which is the temperature at which we're rejecting heat, is colder. And so we can have a little bit lower back pressure on the turbine. And so we can make a little bit more power. And this is where the thermodynamic theory would predict that. So we just need to have those two things kind of firmly entrenched in our mind, not necessarily that we are able to change it, but just so that we understand the potential is there if we could figure out how to do one of these two things. Okay, another way to think about improving thermodynamic performance of power cycles as measured by increased thermal efficiency would happen if we could reduce irreversibilities and losses. So if we insulated better and lost less heat from the piping and the turbine and the shell of the boiler, we'd have better performance. If we could decrease the pressure drop through the piping, you know, perhaps, you know, we put in a larger diameter, but, you know, of course, this would have to be designed in on the front end, but the design engineer has to decide what diameter pipes he's going to put in. Does he put in a 10-inch, 12-inch, 14, 16? I mean, the larger the pipe, obviously, the more it costs, but also for a given flow, the smaller the pressure drop and the better the performance. So all of these are optimizations that have to be determined. At what point does it not make any sense to make pipe larger or to make insulation better or anything that we can think of that would reduce an irreversibility or a loss. The extent of improved power cycle performance is limited, however, by constraints imposed by thermodynamics and economics. That is for sure. The economics, well, I mean, you can't bust the first and second laws, but also the economics. At what point are you just not willing to spend any more money to make it a little bit more efficient? And I must say, if you visit the plants these days, their emphasis is not on efficiency at all. It's on reduced emissions. Reduced emissions is the tail that's wagging the dog, for sure. And, you know, I'm not saying that's not appropriate, but if you had gone to these plants 20, 25 years ago, the whole story would have been, hey, what can we do to become more efficient? And now in today's environment, it's what can we do to emit less to the air or the water or the soil or whatever. So that's job one. Okay, each unit mass water circulating through those components that we have defined undergoes the Rankine cycle. And of course, I think we're pretty familiar with the four principal control volumes involving the equipment here. So, we got the turbine, we got the condenser, we got the pump, and we got the boiler. So that's pretty simple. In these slides, all energy transfers by work and heat are taken positive in the directions of the arrows, and all the equations and balances are written accordingly. So, we have our formal thermodynamic definitions of negative and positive heat transfer and work. Sometimes they violate this, and so whatever direction the arrow is, we're taking it to be positive. So the processes of the Rankine cycle are, well, we know the turbine 1 to 2, so we wind up with fairly high pressure, high temperature steam, vapor, and we let it expand, we let the pressure drop. As the pressure drops, the working fluid expands. So that's one of the terms used for vapor expanding through the turbine to develop work. Then we have to condense it to a liquid by heat transfer to cooling water. And we got to pump it back to the boiler. That requires a work input. So say we'll wind up with a positive, a work going in, work coming out, and then 2 heat transfers. And then in the boiler, we have to transfer heat to it to evaporate it or superheat it, whatever the case may be. Engineering model. Each component we typically analyze as control volume at steady state, which is nice. The transient stuff, the power plants are basically kind of steady state devices. They move around, load moves around and all that, but not all that quickly. And they're so big and so massive that it's hard to make a really quick change. Turbine and pump operate adiabatically. That's a fancy word for no heat losses. So the insulation is ideal in our typical engineering model, unless you're told something differently in a problem. Kinetic potential energy changes are ignored in the first law, which is real nice. Now, every once in a while we'll work a problem and we may put kinetic energy back into it. And of course, if you go to work for GE or one of the big power companies that have the big computer codes, well, they're not going to ignore kinetic. Well, they probably ignore potential energy, but they're probably not going to ignore kinetic energy. Excuse me. Applying mass and energy rate balances, and I'm sure you recall this from your thermo, the first law under these set of assumptions turns out to be pretty easy for the resulting equation for each of our 4 components. The total work out of the turbine divided by the mass flow rate through the turbine is just the enthalpy difference. This is for a simple small turbine without extractions or anything. Then if there were extractions, we'd have to modify the equation to take that into account. Condenser, the total heat transfer rejected per unit mass, just enthalpy difference. The pump per unit mass flowing through it, pump work per unit mass flowing through it, just enthalpy difference. And guess what? The boiler heat transfer in per unit mass is just enthalpy difference. So if you can remember enthalpy difference, you're in pretty good shape on these components. Performance parameters, thermal efficiency. Well, we had the first part of that equation, the net work of the cycle, well, divided by the total heat transfer added in the boiler. So that's the turbine work per unit mass minus the pump work per unit mass, both as positive quantities, divided by the boiler heat input per unit mass, and then we have definitions for the simple cycle that we can plug in terms of enthalpies. So, you know what, H1 minus H2 is the turbine. So that's going to be positive because you have more energy at 1 than you do at 2, minus the pump. So that's written the exit energy of the fluids are going to be greater than the inlet because the pump's doing work on the fluid. So that's a positive. And then at the boiler, that's the exit steam from the boiler at 1 minus the feed water at 4. So those are all going to be positive quantities. Back work ratio. This is one of the parameters that we can calculate. It's what's the work required by the pump per unit mass divided by the work produced by the turbine per unit mass, and then the enthalpy definitions. That's one of the big advantages of a Rankine cycle over a Brayton cycle. We're pumping water. And so you put water in a pump, you don't have to put all that much energy to increase its pressure. Brayton cycle is trying to move a gas, trying to compress basically air. And that's a very inefficient process, increasing the pressure on a flow of a gas compared to a liquid. Back work ratio is characteristic low on vapor power plants. Example 8.1 is referring back to your thermo book. The power required by a pump is less than 1% of the power developed by a turbine. Well, that's extremely good. We can have 30, 35, 40% back work ratio on a gas turbine cycle. Okay, let's see. The provided states one. Those are the states around, you know, out of the boiler into the turbine, out of the turbine into the condenser, and across the pump. So long as, I mean, you have to know those state points, but then we can use the equations to determine the performance of a Rankine cycle. This is an important note. Since these equations are developed from mass and energy balances, they apply equally when irreversibilities are present or for idealized performance. So we can still use those equations in either case. And, you know, we'll develop the assumptions around the ideal Rankine cycle here in just a minute. And then later on, we'll probably work some problems that have some actual state points that would include irreversibilities in them. But those basic equations hold in either case. Okay, here we go. Let's define the ideal Rankine cycle. Well, the ideal Rankine cycle provides, it's a simple setting to study aspects of vapor power plant performance. Ideal cycle adheres to the following modeling assumptions, which of course are not going to be completely true in a real world type device. Frictional pressure drops are absent during flows through boiler, condenser, through piping, that sort of thing. And these processes occur at constant pressure. So we saw in that first diagram, we were looking at how the reheat pressure dropped in the piping as it went back to the boiler, and then it seemed like it was 40, 45 PSI drop in pressure in the real cycle diagram on that first slide. And if we're working, you know, an ideal Rankine cycle problem, we would just ignore that sort of pressure drop. So that's one of the assumptions we make for ideal Rankine. Flows through turbine and pump occur adiabatically and without irreversibility. And if you remember our definition, adiabatic, reversible. So without irreversibility is a double negative, which means it's reversible. Adiabatic reversible is isentropic, which means the entropy is constant across the turbine and the pump in the ideal Rankine cycle. Now, not so in a real device. Okay, but we'll pursue this ideal Rankine cycle, and then we'll allow it to be modified into real world type devices. The ideal Rankine cycle consists of 4 internal reversible processes. And now we'll see it on a TS diagram is probably the most advantageous diagram to plot this cycle up on. It's the one that's used most of the time. So the isentropic expansion through the turbine, there you go, from 1 to 2. Now, if we were superheated, then we would be going from 1 prime to 2 prime, okay? Now, if you were to just compare this state 2 with this state 2 prime, one of the big differences is there's a whole lot more moisture, right? The quality is much less at 2 than it is at 2 prime. If I could get all the way, fall down right on this point, you know, right on the dome, then there wouldn't be any moisture present, because that turbine doesn't like water droplets inside it. The low pressure turbines typically have some, but the more we can reduce that, get it close to 0, the better we are. And so one of the big benefits of superheating is to, and remember, this is an isobar, this is a line of constant pressure. So we have the same pressure from 4 up to A, over to 1, and even up to 1 prime and on up on this line. So that's a line of constant pressure on a TS diagram. Likewise, this is the condenser pressure down here, and it's the same, and actually it trails off over here into the compressed liquid region as well. They just didn't draw it. Okay. And so we're saying isentropic, which means, well, this axis is entropy. And so for isentropic, we're going to drop straight from whatever point we enter the turbine straight down to the condenser pressure. Okay. And so with no entropy increase. Now, a real turbine will have some entropy increase. And so if you started at 1, you'd have to wind up over here to the right of 2. If you started at 1 prime, you'd have to wind up over here to the right of 2 prime, which in terms of moisture in the turbine actually helps you, right? So the irreversibility involved in the turbine reduces the amount of work that you can get out, but it does help in terms of eliminating moisture, because if we come straight down to 2 prime, I've got more moisture than if I bend over here to the right a little bit. I'm getting closer and closer to a quality of 1. Okay, process 2 to 3 is heat transfer from the working fluid passing through the condenser at constant pressure. Now, in reality, there would be some pressure drop through the condenser. Oops, went the wrong way. There we go. From 2 to 3. If we were superheated, then we would be going from 2 prime to 3. And we're showing that just to the dome, which means it's all saturated liquid. Probably in reality, we're going to go over here into compressed liquid a little bit to make sure that we don't put any vapor into that pump. Pumps don't like vapor, just like turbines don't like water droplets. And so that would, slugging that pump is not going to help it. And then we have the isentropic compression in the pump. So again, we're ideal. So we're going to go straight up from the condenser pressure to the boiler pressure, to the pressure of the, to this isobar up here. And that's just heating the liquid, or no, that's not heating, that's compressing the pump, increasing the pressure. It's really the pump in the Rankine cycle that establishes the high pressure that is maintained in the boiler. You have to, because of pressure losses, you have to pump it to a higher pressure than you really want inside the boiler. But it's that pump that establishes that pressure. And then we have heat transfer to the working fluid passing through the boiler at constant pressure. So we're going to go from 4 to A to 1 if we're going to stop at superheated I'm sorry, at saturated vapor. If we were going to superheat, then we would keep it in the boiler longer, heat it up more at the same pressure, and then we would rise up to 1 prime. Okay, possible variations. We talked about turbine inlet state, superheated vapor, been all over that. And pump inlet state, state 3 falls into the liquid region. Again, this condenser, we're gonna get it over here someplace to make sure that we protect the pump. We go straight up to there. Okay, since the ideal Rankine cycle involves internally reversible processes, the result, this is from section 613 in your thermal book. We'll see the result is applying equation 651C, the pump work per unit mass flowing through is evaluated as. Okay, so you need to note this equation. So the isentropic work, if you go back and look at 651C, what you see is that the work required by the pump or done on the working fluid by the pump per unit mass is the integral from the inlet to the outlet stage of the pump of VdP for an isentropic pump. Well, you see, that's not, we don't show the integral, we show the specific volume at 3, which is the inlet times the delta P, P4 minus P3. Well, what's happened is we have assumed incompressible, that the water is incompressible, which means that the specific volume at 3 is roughly constant, which means it pulls through the integral. And so you wind up with specific volume as a constant times the integral from, in this case, 3 to 4, because those are our subscripts, the integral of dP. Well, integral of dP, I can integrate that. That just integrates into P evaluated at 4 minus 3. And so you get the specific volume at 3, which is considered constant. But it's, in reality, it's not completely constant, but we usually take it, the convention is we take it at the inlet. So that's why we show the specific volume at 3 times the pressure difference, the pressure increase in the pump, because P4 is greater than P3. So that's going to give a positive number. Now that's the isentropic work. So if you have an isentropic pump, then you're done. If you don't have an isentropic pump, then we have to use the isentropic efficiency equation for the pump to adjust the amount of pump work, which means if it was 70% efficient, then we'd have to divide by 0.7 to get the appropriate amount of work. So let's see, so we're saying there where little v sub 3 is the specific volume at the pump inlet, and S is isentropic process. So you need to note that, and when we start working problems, that's what you will typically use that equation to work across the pump. What the way it usually works is we know the enthalpy, we know the condition into the pump, and we use this to help us calculate the enthalpy at the exit of the pump. Because remember, pump work per unit mass is also what? H4 minus H3. So then if you take that and you add H3 to it, you get H4. So that's a way to evaluate that enthalpy. Okay, we'll see more of that as we start working problems. Okay, so applying equation 649, areas under the process lines on the TS diagram can be interpreted as heat transfer. This is for the ideal Rankine cycle only. So we have the area representation on the TS diagram. So for example, if we want to look at heat transfer for the water flowing through the boiler, we can look at area 1B, C, 4A1. So that's the shaded area. So now that's not if it was a rectangular area, it would be real easy to calculate from the TS diagram if you just knew the the parameters, the state points on the cycle. This one would be a little bit harder because it's not just a rectangular area, but nonetheless, that's what that area, and it's all the way down to the S-axis is the boiler heat transfer, heat added in the boiler. Okay, and then we can also look at the area that represents heat transfer from the water flowing through the condenser, and that's this little box down here. And you can see that's area starting over at 2BC32. So there you go. And then guess what? The area enclosed by the cycle, 1, 2, 3, 4A1, represents the net heat input, which is, we know for the cycle, is equal to the net work developed by the cycle. And so that's the area enclosed by the cycle. So those are the area representations of heat transfer, again, for an ideal Rankine cycle. For a real cycle, that's not correct. Okay, how are we doing? Let's do a time check. What do we got? 2:04, so we still got a ways to go here. So using the ideal Rankine cycle to study the effects of performance of varying condenser pressure. Okay, so now we go through these kind of thought processes of thinking what would happen if we could make some of these changes. So the figure shows two cycles having the same boiler pressure but different condenser pressures. So we see this, say the initial cycle, 1, 2, 3, 4, 1, and it's showing the condenser pressure to be just atmospheric pressure. And so we see at atmospheric pressure, we see that heat transfer occurs at 100 degrees C, because that's the saturation temperature that goes with 1 atmosphere of pressure, okay? Well, let's say we figure out somehow we can modify our cycle and we can drop condenser pressure, which then would drop condensing temperature. And we know that if we reduce the average temperature during the heat rejection and keep the rest of the cycle the same, that's going to help our efficiency. So somehow by hook or crook, we've managed to basically be able to transfer this heat at a lower temperature than we could before, which allows us to drop condenser pressure from P atmosphere to a pressure less than P atmosphere. And, we kind of exaggerated it probably a little bit here, but so then this is the lower pressure. So then you can see that our turbine would then go from 1 to 2 prime. Well, you can see that's going to be significantly more work output from the turbine. And then we're going to reject heat from 2 double prime to 3 double prime. We're going to pump to 4, and then the boiler is going to heat all the way up back to 1. Well, and you kind of see, I mean, we're putting a little bit more heat into it. The boiler heat before was what, 1 down to the axis, over, up through 3 to 4, and then close it out. Now, the boiler heat input is again 1 down to the axis, over to 3 double prime, up to 4 double prime, and then back. But we also see we get a significant increase in area enclosed by the cycle, so we're getting more work out of the cycle. And the theory tells us that this will enhance or help our thermal efficiency. Let's see, before we do that, the other thing to think about is, what about moisture in the turbine. So what happens to the quality as we go, you know, at state 2, we had a bunch of moisture, but at 2' we have a bunch more moisture because you can see the quality is dropping because relatively speaking, we're further in toward the center of the dome when looking at this lower pressure compared to this one. So I would say that the amount of moisture in the turbine is increasing, so that's hurting my turbine. It's helping my efficiency, and so I'm getting a little more work out of it per unit of fuel input. So that's the way these changes come, with pluses and minuses. And then we have to try to figure out maybe some other things we can do to get rid of some of the minuses, keep the pluses and moderate the minuses. Okay, so one is at atmospheric pressure, the other is less at atmospheric, and of course we can do the little animation and we get there. Okay. And so this slide is referring back to the same situation. And we notice that the temperature during the heat rejection is much less than 100 degrees, which it was initially. And so that's what's going to tell me that I'm going to help my efficiency. Since the temperature of heat rejection for cycle 1, 2', 2 double prime, 3 double prime, 4 double prime, 1 is lower than for 1, 2, 3, 4, 1. The cycle condensing below atmospheric pressure has a greater thermal efficiency. Reducing condenser pressure tends to increase thermal efficiency. So these are the types of understanding that we want to kind of let this soak in so that this becomes part of us when we think about the Rankine cycle. Okay, power plant condensers normally operate with steam condensing at a pressure well below atmospheric. For heat rejection to the surroundings, the lowest feasible condenser pressure is the saturation pressure corresponding to the ambient temperature. And of course, that's not even really feasible, because if you're right, I mean, if you're at the same temperature as the surroundings, then it takes an infinite amount of surface area to transfer a finite amount of heat. And so really, let's say if you're transferring to a lake, maybe in the summertime, that lake gets up to 65 degrees, something like that. Then if your condenser pressure is what, I don't know, what 1 PSI, we're someplace around 110. I'm sorry, it was 101. At 1 PSI, it was, I think, 101.7 degrees Fahrenheit. So if you're trying to reject to a lake that's a maximum of 65 degrees Fahrenheit, then you've got what, a 35, 36, almost 37 degree delta T. Then you don't have to have just a huge condenser. Relatively speaking, it can be smaller because you have a reasonable temperature difference to make that work. Of course, it also increases the irreversibility of it, but that's just the way it is. The primary reason for including condensers in vapor power plants is the increase in thermal efficiency realized when the condenser operates at a pressure less than atmospheric pressure. So what they're saying is you get a bigger delta P across your turbine, and the bigger delta P across the turbine, the more power you get out. And that's certainly true. Another is that the condenser allows the working fluid to flow in a closed loop. And so demineralized water that is less corrosive than tap water can be used economically. It's also warmer. And so that would reduce boiler fuel a little bit. It has chemicals added to it, and you just can't afford to throw all that away. There's so much water passing through a good sized power plant that you have to reuse the working fluid. You only make up losses, boiler blowdown and leaks and steam leaks or water leaks, that sort of thing. As steam condenses, energy is discharged by heat transfer to cooling water flowing separately through the condenser. Okay. Although the cooling water carries away considerable energy, its utility is extremely limited because cooling water temperature is increased only by a few degrees above the ambient. Such warm cooling water has little thermodynamic or economic value. And we talked about that some. That's the idea that we only have one product coming out of a big power plant, electricity. And so we have optimized the cycle to maximize the power generation, even though in doing so, we pull that pressure and temperature of all that 40% of the energy and the fuel down to such a low level, it's not useful for anything. And see, this again feeds back into the cogeneration argument. Whereas if I come out of that turbine at 200 psi G, I've got enough temperature that I have steam that's useful to do something for me if I have a secondary product, if I have something else to be done. So anyway. Okay, the figure shows two cycles having the same condenser pressure, but different boiler pressures. So now we're going to look and see what happens if we could increase the boiler pressure. Well, you can see, let's just go around the cycles. We have our same initial cycle, 1 to 2, the turbine, 2 to 3, the condenser, 3 to 4, the pump, and 4 to 1, the boiler. And now we've gone up in boiler pressure. So this is a higher isobar up here. So now we're going to operate from 1 prime to 2 prime, from 2 to 3, from 3 to 4 prime, and 4 prime to 1 prime. Well, okay, so first of all, I always say, what's the turbine say? And the turbine says, ouch, I don't like it, because you're allowing much more water to condense inside the turbine. What's going to come out as droplets? It's going to go through those blades that are spinning 3,600 RPM, and you're going to damage your turbine blades much quicker than you would with less water in the machine. So the turbine doesn't like this. So we're showing here our initial boiler pressure, and then we're going to go to a higher pressure up there, just to illustrate the change in the cycle. Let's see, is there anything else we need to say there? You can look at the areas under the curves to see. The theory is going to tell you that we get an increase in efficiency because the average temperature during the heat addition, well, in the initial cycle, the heat is added from 4 up to the saturation dome and over to 1. So if you can average the temperature across there, it's someplace down, you know, I mean, we have a low temperature here, we get up to saturation, and then it's constant as we vaporize. Well, in the modified cycle with a higher pressure, we're going from 4 prime all the way up to here and then across here. So it's pretty easy to see that the average temperature during the heat addition is higher if we increase the boiler pressure, and so that's going to help my cycle efficiency. So that's what he's going to point out here. T average from 4 to 1 would be at roughly that level, and T average from 4 prime to 1 prime would be a higher average temperature, so that's going to help me. Since the average temperature of heat addition for cycle 1 prime, 2 prime, 3, 4 prime, 1 prime is greater than for cycle 1, 2, 3, 4, 1, the higher pressure cycle has greater thermal efficiency. Increasing boiler pressure tends to increase thermal efficiency. So that's what we're trying to pound home, but the turbine doesn't like it. Okay, and this is where he's making the turbine issues. However, the increase in boiler pressure also results in a reduction in steam quality for the expansion through the turbine. Compare the lower quality state 2 prime with state 2. And that's what he's going to do. We're going to slide down there. So there you go. We got the quality at 2 prime being less, so we have more moisture. If the quality of the expanding steam becomes too low, the impact of liquid droplets in the steam can erode turbine blades and possibly diminish performance. Absolutely. That turbine's not going to be happy at 2, much less 2 prime. Rankine cycle modifications known as superheat and reheat permit advantageous operating pressures in the boiler and condenser while avoiding low quality steam in the turbine expansion. So say, so we're going to go ahead and lower the condenser pressure as low as possible, raise the boiler pressure as high as possible, but then we're going to do other modifications to the cycle to mitigate this potential negative impact. Another such modification is the supercritical cycle. All three are considered next. Okay, so the figure shows a Rankine cycle with superheated vapor at the turbine inlet. So, we kind of talked through this before, but so if this is into the boiler, if we're going to superheat, we just stay at on that same isobar. And once we get beyond this point, we continue to heat, we get an increase in temperature at that same pressure. So we wind up here at 1 prime. So T average 1.4. So you can see that from our discussion of average temperature during the heat addition, this has to help the efficiency, right? Because if I heat from 4 to 1 prime, my average temperature has to be greater than if I heat from 4 to 1. I think that's pretty clear just by looking at the diagram. So the cycle with superheat has a higher average temperature of heat addition than the cycle 1, 2, 3, 4, 1 without superheat. Thus, we have a better efficiency. Moreover, look at the turbine. Wow, the turbine's getting happy. The turbine's getting much, much happier. Right. Turbine likes 2 prime compared to 2. Moreover, the superheat quality at the turbine exit state 2 prime is greater than that at 2. The turbine exit without superheat. So this superheat's a good deal, right? It helps the efficiency and it helps the turbine. And we're going to slide the little X's around there. Okay. A combined boiler superheater is called a steam generator. That's your author's terminology. The boys in the business still call them boilers, but whatever. Ideal reheat cycle. The reheat cycle is another Rankine cycle modification that takes advantage of the increased thermal efficiency resulting from a higher average temperature of heat addition, and yet avoids low quality steam during the expansion through the turbine. So what do we do here? Well, let's take a look at it. Look at it on the diagram. So we come out of the boiler, main steam flow at 1, enter the turbine. Come out of the first turbine section, or we're going to call this the high pressure turbine, after, we're not all the way down in pressure or temperature, but we're going to go back to the boiler. And of course, for our ideal cycle, we're showing constant pressure. In the real cycle, we do have some pressure drop associated with this, but we're going to heat it back up again, much warmer. And then we're going to go back to a second, our low pressure turbine, and expand some more to get some more work out before we go to the condenser. So if we look at this, our feed water pump is 6. So while we're coming into the pump at 5 out of the condenser. So into the pump, out of the pump. So from 6 to 1, we're going to superheat. We're going to come all the way up here to T1. Okay, and then we're going to expand through the high pressure turbine, and this is isentropic, so we're going to drop straight down to this intermediate pressure, and then we're going to go back to the boiler and we're going to reheat. I know the Kingston cycle showed these two temperatures being the same. This diagram shows it being a little bit less. It just depends on the cycle design, but we're going to pick up temperature at this intermediate pressure, and then we're going to drop through or expand through the second turbine down to 4. And so, well, that does a couple of things, right? It increases the average temperature of the heat addition, because now instead of just heating here to here, we come back and we're going to do this little whoop-de-doo in here, which is at fairly high temperature. So that's going to increase my average temperature heat addition. And instead of coming out of the low pressure turbine at 4 prime, I'm going to come out at 4, which means I have less moisture. So the reheat is a win-win. So I got superheat helping me, and then I can add reheat that can help me further. With reheat, the steam quality at the turbine exit state 4 is greater than at state 4 prime. Get that off of there. The turbine exit without reheat. So if we don't do the reheat, we just have to go through both turbines. And if they're isentropic, it's a straight drop. But if we do the reheat, then we get to jog over here and down. Thus, we get less moisture. So that's pretty good. Oh yeah, we got to do the animation here. Bingo. Departures from the reheat cycle from the simple vapor power cycle considered thus far include process 1 to 2, steam expands through the high pressure turbine stage. Process 2 to 3, steam is reheated in the steam generator. And process 3 to 4, steam expands through the low pressure turbine. So we're adding some hardware, right? There is some expense to this, right? We got to have a reheat section. We have to buy a more expensive boiler that has not only main steam, superheat, but an additional reheater section. And then we buy 2 turbines that are split apart. That's going to be more expensive than just one turbine. And we got the piping and all that. So there is additional expense to this. When computing the thermal efficiency of a reheat cycle, it's necessary to account for the total work developed into turbine stages, right? I mean, we've got 2 turbines, so you got to calculate the work produced by both. We still just have 1 pump, but we got 2 turbine sections. So we got to do 1 to 2 for the high pressure, and we got to do what, 3 to 4 for the low pressure turbine. Total heat added during vaporizing, superheating, and reheating. So we also have additional processes in the boiler. So 6 to 1 is the main steam heat addition, and 2 to 3 is the reheat steam addition. So our thermal efficiency is getting a little more complicated. So we've got the total work out of the high pressure turbine plus the total work out of the low pressure turbine, subtracting off the total pump work, divided by the heat addition to the main steam and the heat addition to the reheat. And you could do that all per unit mass if you wanted to. They're showing that with just totals. Okay, let's check time here. Okay, we'll do a little bit on superheat, ideal reheat cycle, and then we'll supercritical rather, and then we'll cut this off for this lecture. Steady improvements over many decades in materials and fabrication methods have permitted significant increases in maximum allowed temperatures and steam generator pressures. So the old mantra for years and years, make it hotter and increase the pressure and you get more efficiency out of the unit, so long as it doesn't destroy itself. So it's materials. These efforts are embodied in the supercritical reheat cycle. And so here you go. Look at this one. So now it's pretty similar, except this pump, this is a big boy. This is a big boy pump, right? It's going to pump up to a pressure greater than the critical pressure. So critical pressure, I think it's 3206. You can check me on that, but someplace real close, 3206 PSIA. So that might be 3,800, that might be 4,000 coming out of this pump. So this is the isobar, and it never touches the dome. So there is no phase change from liquid to saturated vapor. It's just all fluid. And as we heat it, there's this just general transformation. So let's see. There we go. So now we're up in supercritical land, and then we're going to expand down. So no phase change occurs during process 6.1. Instead, water flowing through the tubes is heated from liquid to vapor without the bubbling associated with boiling. So it's just not a boiling process. There is a transformation, but it's not like boiling. Bingo. And then, of course, we're going to drop down to 2, and then we're going to go back and reheat, and then we're going to drop into the dome with a second turbine. Today, supercritical plants achieve thermal efficiencies up to 47%. Ultra supercritical plants capable of operating at so higher temperatures and steam generator pressures will have thermal efficiencies exceeding 50%. But I'll tell you, TVA had a supercritical plant at Bull Run, which is north of Oak Ridge. And for years, Bull Run was one of the 2 most efficient coal plants in the country because it was a supercritical unit. Well, about, I think year 4 last, TVA up and shut down Bull Run. So that was a real piece of news to the industry, saying that, hey, we're going to eventually walk away from coal. So they're trying to walk away as fast as they can. It's just there's so many generating assets out there that are still coal-based. You just can't make the conversion instantly. It's going to probably take, it'll probably take at least another 10, if not 15 years to pretty much wean us off of coal. TVA will be one of the earlier utilities off, mostly because of, I'd say, watch bar 1 and 2. And I mean, they're putting resources into solar, but we also have hydropower. And so hydro, what do we see? Was it 10% hydro, 20% nuke, something like that. And then, of course, we're growing natural gas fleet pretty quickly at the expense of the coal fleet. But it's going to be interesting to see, because it looks like the Biden administration is going to attack fracking. And if they do, the price of natural gas is going to go up significantly, which means your electric rates are going up, and certainly in Tennessee. And there will be, I'm not sure where the scramble will go next. It takes a lot of acreage for solar photovoltaic, and nuclear is just forever and a day to build. If we have to convert to nuclear to avoid fossil fuels, it's going to be expensive, and it's going to take probably 15 years for Tennessee, at least, because it just takes such a long time to get approvals, to get permits, and to build and operate and open up a nuclear plant. So it'll be interesting to see what develops. Okay, this is a great place to stop. So I'm gonna stop right now, and I'll ask if there are any, I'll stop the share. Does anybody have any questions or comments? I'll be more than happy to. We still have, some time. We got close to 15, 20 minutes left in class, but I don't want to drone on anymore with you. So if anybody has any comments or discussion, unmute yourself and please jump in. Or questions on homework. For the homework, what schedule? Well, you're given contract demand. So that's part of the homework. That's a good question. But I've looked at so many of those. Was it 9,000? Was the contract demand on this one 9,000?
Yeah.
Okay. So look, in the discussion of the rates, you've got A, B, and C. And so A refers to a certain capacity of plant, B a little bit larger, and C larger than that. So you can determine that from that contract demand. Good question. In other words, I'm not gonna tell you, I'm gonna make you figure it out. It's pretty straightforward. I had chat. I'm not good at looking at chat. Oh, okay. Oh, that's fine. No, I mean, that's, hey, the idea is to learn. Now, there's, those assignments seem simple on the front end, but when you have to start tearing down into all of that detail, I mean, they're, after you've done a couple of them, they get pretty straightforward, but it's good exercise. Welcome to the real world of buying and selling power. Anything else? All right. I guess I'll let y'all go. Hope everybody has a great rest of the day. Laurie, I hope you have a good trip. Wish I could go.
Thank you. I know.
All right. I guess I'll cut this off. Stop the recording here if I can figure out how.